So it's a pleasure to present the next speaker, Camila Machado, who will tell us about soft theorems and massive recursion relations. So please, the stage is yours, Camila.
So thank you very much. Thank you for the organizer for the invitation. So today I'm going to talk about this paper that I did in collaboration with Adam Volkowski. I'll be talking about soft amplitudes, which means that I'm taking amplitudes with n legs, and one leg will be in general a soft photon or a soft graviton. And the momentum is going to go to 0, and we are going to look to the expansion in the soft momentum, and in particular to the relation between the amplitude with the soft particle and without the soft particle. And this soft amplitude has a really rich and interesting story. There's some connection with basic properties, such as charge conservation and the equivalence principle. And there's also this beautiful connection with asymptotic symmetries, and also with the Adler zero and the construction of the special EFTs. So in particular in the soft graviton, the leading term was known for a long time. And the subleading and sub-subleading was more recently. And in particular, the recursion relations played an important role to explore these soft theorems in a quite systematic way and lead to the kind of discovery of the sub-subleading piece. And also more recently, in this paper by Wang, Jones, and Makulish, they also use the recursion relations, but this time a combination of a soft shift with a kind of BCFW shift to also explore how effective operators change these soft theorems. And what they found that is in this case, they can, some operators can indeed modify the sub-subleading soft factor. Now, most of these these studies with recursion relations assume massless particles. And we decided to think what we can do to really include the massive particles. So the first step is like, can we just write the recursion relations using massive spinors, and what we can learn from the soft theorems when we include the masses. So this is what I will talk today. So first, I will discuss how we kind of extend this idea of having this soft plus BCFW shift that was already discussed by Wang and collaborators, but now we allow for also massive particles. And then I will discuss how the soft theorems now using these massive spinors, how is the form that they take. Especially in the case of the gravitational multipole expansion, and I'll talk a little bit about soft exponentiation. And in the third part, I'll talk a little bit about Compton scattering and how there's appearance of spurious poles for higher spin particles. Okay, so for the massive recursion, the idea here is that we allow all the particles to be massive, except of the soft particle that can be in general as a photon or a graviton or a gluon. And we are going to define the recursion relation using two parameters, this epsilon that's going to control the soft limit, and z that's a holomorphic variable that is going to be used to derive the recursion relations. So in general, I'm going to shift this the soft particle plus two other legs, J and K. And we can write the general shift in terms of these two parameters, epsilon and z, in this form. There is this vectors Q that we need to impose that we want to satisfy the on-shell conditions and momentum conservation to find out what exactly this form of this Qs. And now the on-shell condition, it's of course that with the mass of the particles will not change with the shift. So we can solve for the shift spinors Q, and we did all the cases if the particles are massive or massless, and of course when all are massless, we recover the same shift as Elvangen collaborators. And we also use the massive formalism of Cunningham, Wang, and Wang, which means that the SU2 little group index are going to be omitted, and I'm going to use both spinors for the massive particles. So this is kind of one solution for the shift. So it's still, it can be written in terms of arbitrary spinor Y. That's going to be relevant in a few slides, so just highlighting here. We can also do the same exercise in the case that two particles are massless and one is massive, for example. Now, the idea is to look to the poles related to the emission of the massless particles from external legs. So we want to look at these poles in the P0L, and they occur in this position ZL that are proportional exactly to the parameter epsilon. So you can do the usual story with the Cauchy theorem to find out that the recursion relations in this case can take this form, where here you have the 3-point amplitude and here the any point amplitude. And since these poles are proportional to epsilon, it appears the expansion in the soft momentum. Now, if the recursion relations, there is a boundary term, it's going to appear at the order epsilon 0. So this will not be a problem to describe the amplitude in the soft limit. Okay, so now we can, given that we define this massive recursion relations, we can work out some specific cases. So here I'm taking just minimal gravity. So the 3-point amplitude with two particles of spin S and a graviton. And this factor is what in general in the literature is called the X factor. And then we can just apply the shift and plugging in the recursion formula, expand both sides in epsilon and see how it works. What are each soft factor associated with each power of the epsilon expansion. So this, not a surprise, it's a universal soft factor, so not expect that will change just having the massive particles. And here there is something curious that the soft factor appear to have a dependence on this Y spinor, which seems weird, but then you can check that indeed, when you assume equivalence principle and the momentum conservation, this dependence drop out. So otherwise you can think it the other way around, that by consistency, to be independent of this Y vector, we can derive the equivalence principle. Going to the subleading soft factor, now what appear is a differential operator that we can write in this form. So appear some derivative in terms of one of the massive spinors. And here, if you again has this apparently dependence of these arbitrary spinors, but when you check, you can rewrite this using the angular momentum operator, and the conservation of the angular momentum guarantees that this dependence of the Y spinors will drop out when you do the sum over all the legs. Now the subleading one, what happened is that these differential operators appear square. Now it is actually independent of y, so apparently it's not, we cannot derive any other constraint from it. Okay, so the next thing that we can do is, let's say, include a gravitational dipole coupling and see what happens. So in this case, you can again just do the same exercise with the recursion relations. You're going to see that this first piece doesn't modify, but the second piece indeed has some modification. You have this term that's proportional to just the gravitational dipole. But you can verify that there is no way to drop this dependence of this reference spinor unless the dipole coupling is zero. So this would be another way to really show that the gravitational dipole coupling is not consistent with the basic assumptions of unitarity, locality, and Poincare invariance. We can, since the dipole doesn't exist, we can go to the next, that is a gravitational quadrupole. And the other terms in the multipole expansion actually will not affect the soft theorems. So for the quadrupole, what we have is that again there's no modification in this induced in the leading and sub-leading piece. And in the sub-leading one, indeed, we can compute what is going to be the soft factor induced by this gravitational quadrupole. And in this case, it's a bit different from the others because here you really appear a non-trivial dependence of this massive Lyra group structure. The other thing that we could see that once you have set up these recursion relations, kind of easy to prove, is that if you take the 3-point amplitude for, you can take any at least for the massless particle, using the recursion relations, you can show that the whole thing exponentiates in this form. And this is just was extending a proof that was already in the literature, but was made in the case of just the image V sector, so just massless particles. The case that we want to include the electromagnetic dipole or the gravitational quadrupole, we can just change this differential operator to include also these extra pieces in this form. Now, just want to discuss a little bit about the Compton scattering. So another thing is that the emission from external legs accounts from all factorization channels. So this means that we can just recover not only the amplitude in the soft limits, but the full amplitude. So in this case, we can write, here I'm writing the Compton for photons, but similar can also do with gravitons. And we can write where this is the soft factor that appear and this 3-point amplitude, we can compute using the shift spinors and take also this form. So in this case, if you want to take the full amplitude away from the soft limit, you can just set this parameter to 1. And this would be similar as doing something like a BCFW shift to compute the full amplitude. So I'm not going to enter in details, but in the paper, we also computed the 5-point amplitudes, including 3 photons or 3 gravitons. And also the 4-point amplitudes, including the dipole and quadrupole couplings. There's just one parenthesis that I want to comment, is that you can also write the 3-point amplitude in terms of the angular momentum, like this. And using the recursion relations, we could show that the Compton amplitude can take this exponential form, which is particularly useful in the context of black hole scattering. And the use of the recursion relations make one derivation of this that appeared in this paper by Guevara, Oshirov, and Vines a bit more clear, because they kind of have to make a choice for this reference spinner that's not so directly as doing with the recursion relations. So there is one thing that the recursion relations don't solve is the problem with the spurious poles that appear for higher spin. So here this A and B is just like some spinor combination. And the thing is that for higher spin, this piece 3p14, it's gonna appear as a spurious pole. So in principle, you need to add a non-zero boundary term to cancel it. And this was already discussed in this reference, but we also give you a try to write these boundary terms in a kind of let's say more concise way. So the trick that we realize is that this problem gets much simpler if you're working out with the right variables. So if this A and B are these spinor combinations, and we define some other variables X, Y, and Z that are also some other spinor combinations. But the trick is that they are related with some useful identities that always appear together with this 3p14, that is this spurious pole that appear. And these make the problem of canceling this pole just kind of like playing with polynomials in these variables. So just to give a more concrete example, you have the, in this case of the spin 2, you get like this formula, and you can, when you rewrite this A and B in terms of these other variables, and what this helps is to see exactly how is this, the terms that appear with the spurious pole and how you can cancel it. So here there is a double pole and another simple pole, and there are some other terms that appear that actually don't have unphysical poles. So this just helps you to make it more evident what are the terms that you need to really cancel. So in principle, you would just write the polynomial that cancel this directly. But the thing is that this can mess up with the T and U poles, which you don't want to do. So this that enters in the game, these other relations with these variables, that you can really find a way to write a combination that cancel this y to the 4 and xy to the third power in a way that you don't mess up with the T and U poles. There is one thing that appear here that is the solution is not unique, because you can add a pure contact term that will not made anything with the pole structure. And recently there was some very interesting discussion about how some extra conditions in the amplitude can also fix this contact term, at least in the case that for certain spins. We just did something a bit different. We just looked to what is the energy growth of this contact, this boundary term. So in this case, one can see that it grows as e to the 8. And since this is the higher spin particle cannot be elementary, and this we are talking about EFT, This energy growth is just associated with the loss of perturbative unitarity at a cutoff scale that is around the particle mass. So in the EFT spirit, you want to postpone the cutoff as much as you can. And this translated to, you would like to find the best possible behavior for your boundary term. So you can indeed add a contact term that make the whole amplitude grow as a bit better as e to the 6. So in the sense, you kind of your EFT has a larger regime of validity.
Camila, at this point, you have less than 10 minutes, including the questions.
Okay, almost there. So we could perform these steps in a systematic way and construct this boundary term for any spin, and show that this indeed grows as e to the 4s. But we also showed that you can always add a contact term to make this UV behavior a bit better and make it grow as 4s minus 2. And this we can kind of read off what would be the maximum cutoff of the EFT with this particle of mass S and charge Q and spin bigger than 1. So this is what we find for the maximum cutoff of the EFT. And this was also kind of conjecture in another reference that had a different approach looking to actually effective Lagranges, and they kind of find the same bound. Now, I'm not going through the details here, but actually the very similar story follows for the gravitational Compton. We could also find the general boundary term that also has a quite compact form, but again, it's not unique in the sense that you can always add a contact term. And the best UV behavior that we could get is such that we can write the maximum cutoff of this EFT with a particle of mass m and spin bigger than 2 that interacts with gravity to take this form here. And this was also kind of pointed out in other reference that found a similar bound through different techniques. So I think this is what I wanted to say. We constructed this new massive soft plus BCF-Dava recursion relations, so extending what was in the literature for massless particles. And in this way, we could systematically study the soft theorems, including massive states, making the connection with the higher spin amplitudes that are important for the black hole dynamics. And we also had some results for the Compton amplitudes with photons and also with gravitons. And this systematic way to build the contact terms to cancel this spurious poles. That's it. Thank you very much.
Thank you very much, Camila, for this nice talk, and also thank you for keeping the time so well. So let's all thank Camila. And now it's open for discussion. We have about 5 minutes for questions. So who wants to start?
So I could ask a question. So Camila, thank you for the very nice work and presentation. In the massless case for the master formula, we saw that there were constraints that didn't allow higher spin particles to couple to the massless gravitons with canonical couplings. And so do I understand it correctly? So you don't see any constraints when you have massive higher spin, right? And you are, and then do you think there are any ways of putting in constraints of seeing infinite towers of massless particles by putting in some other kind of weak gravity conjectures or other kind of systematics on the EFT coefficients?
Yeah, I think there is no obstruction in the case that you have this tower with massive higher spin particles, and so I mean we don't find any constraint in this sense. What we found with looking this Compton scattering is more. I mean, these theories have to be understood as effective field theories, and in this sense, there is no problem. And what we could see was just this bound of the validity of the EFT. I don't know, I think maybe with some more elements, as you said, with the weak gravity conjecture, maybe there is some extra conditions that one can look for. Yeah.
Thank you.
Any further? Yes. Jan, please go ahead.
Hi, Camila. Thanks for a great talk. I was wondering, with some years back, when we looked at the massless situation, we understood that there are certain constraints for the subleading contributions to the soft theorems arising from the necessity to balance the delta function, the total momentum conserving delta functions of the n+1 and the n particle amplitudes. I was wondering if you looked at that in the context of your situation now with the massive guys.
No, actually, no. Why exactly you have this extra constraint?
Well, because you know, if you start from an endpoint function, you have n plus, or say an n+1 point function, and you take one guy soft. You have to conserve the momentum of n+1 particles. On the other hand, only from n. So there has to be a non-trivial commutator actually of the subleading. So from this you can understand that the subleading soft theorems have to be differential operators, and their form is also constrained by that. Now I was wondering, it's an interesting question how the hell that would generalize to the massive case.
Yeah,
but you haven't looked at that.
No, because in the end we are always looking to the stripped amplitude without the delta functions. Yeah. So we didn't look this, but indeed.
Because back then we could understand that actually there is not much freedom in the form of these subleading guys.
Sorry, I could make you jump in here. So the way Camila is taking the limit is the soft limit is a generalization of what we did in the massless case, where we manifestly deforming the variables in such a way that we stay on shell the entire time. And the way that changes things is that the derivatives that sit in the subleading soft theorems look a little bit different than they do otherwise in the literature, because we're really taking them in this geometric way that preserves the on-shell conditions throughout. So I think there's possibly a relation between that and what you've been doing, Jan.
Okay. Yeah, thank you very much. That I think clarifies the point. So I think we basically exhausted the window. So let us thank Camila again for this very nice talk.
Thank you.
And we are ready for the next